talk for this part with Jason Bell on invariant hypersurfaces.
Hi, thanks to the organizers for the invitation, and some people might have seen this talk before. I wasn't sure what to talk about, and this is what I'm talking about. So this is joint with my friend Rahim, Moosa, and Topaz. So I'm going to just start with, so really this paper really starts with Rahim. So he's really like sort of the driving force behind the paper. And I think his observation was, if we look, well, probably everyone here is hyper aware that there's this analogy between what happens in the difference setting and what happens in the differential setting. And, it's a bit like the analogy between, integers and fpx, where results here have analogs here often, but maybe the proof techniques are different, or maybe they're the same. But in any case, I'm going to talk about one special type of theorem, and the first is due to Cantat. It actually had a predecessor that was with me and my friends Dan Rogalski and Sierra. But I'll state the Cantat version. So we have X, and I'll just make it a projective variety over, say, C, and a dominant rational map and what Cantat was looking at was he was looking at H that are hypersurfaces, and I'll say a bit about what I mean by that, such that H is, I don't know the terminology, I'll say completely invariant under the map phi. So first of all, when I say a hypersurface, H is not necessarily irreducible, and I want all the components to have codimensionality. So all components so that's going to be a hypersurface. And for totally invariant, let me just give an example of what I mean, just to show the distinction. Let's take the map, the morphism P1 to P1, which is just x goes to x squared. And then if I look at F inverse, so F of the point 1, which is a hypersurface, is 1. So this point is invariant. But if I look at the preimage of 1, it's plus minus 1. So it's not completely, I guess totally invariant. Totally invariant. Its preimage is strictly bigger than the variety. So in fact, the only, I guess I'm tied into this completely invariant terminology. Completely invariant hypersurfaces are things built up from 0 and infinity. We have lots of invariant hypersurfaces, right? We can take the union of nth roots of unity, and that'll be invariant, but it won't be completely invariant. So there's only two. Well, two that really build them up. And Cantat's result says there are only finitely many invariant hypersurfaces. Unless And the unless there's some compelling geometric reason why there should be lots of them. And in this case, there's one very easy reason why you could have them. Imagine I have a non-constant vibration, f x to p1, such that this square commutes. Then what this is saying is that phi is preserving the fibers of f. And of course, generically, the fibers will be these codimension 1 hypersurfaces. Will be these hypersurfaces. So we're basically covering x with this uncountable family of invariant hypersurfaces in this case. So unless phi preserves a non-constant vibration. And you might recognize this as the same as in magnetic scaling, right? That you should expect a dense orbit unless there's a real geometric reason why you shouldn't get a dense orbit. Okay. Predating Cantat's result, and probably motivation for Cantat's result, is this differential setting. By the way, I don't know if it's clear. I'm like really tired, so I don't feel like I can think properly for some reason. But I guess I shouldn't have said that, because maybe you can't tell. So, so in the differential setting, there's a theorem due to Joannou, and it has extensions due to Hershkovsky, and then Freytag and Moosa, and then I guess I did work with Rahim and Omar Leon Sanchez, which is one name, and my friend Stefan. These were all around the same type of theorem. And here, what the case is you have, again, some variety x, and you look at its tangent bundle. So we've got a map here. And what we're going to assume is that you have some section from the variety back to the tangent bundle. And maybe a lot of people know this, just in case you don't, I'm going to look at a very specific example where x in some hypersurface in affine D space. And then what is the tangent bundle of x? So it's a subset of affine 2D space. Where the first D guys just lie on x, and then I want this guy to be 0. And I'll again analyze it in light of this version. Notice if I have a hypersurface y of x, well, no, I don't want to see this. I get something like this, but I don't expect my section here, in general, to send y into ty. Okay? So when it does happen, it's saying something very special about the vector field. So when the section maps into here, we're going to think of this as being some sort of invariant hypersurface. So Joannou's theorem says that among these guys, and I should say in this case, you can always restrict to irreducible hypersurfaces. It's the differential case. So Joannou's theorem says either there are finitely many invariant hypersurfaces. There are finitely many invariant hypersurfaces. Unless. And the unless is, again, the same reason. So let me just look at it in our example. So this is a tangent bundle for just a hypersurface, but you can imagine you can just glue these together for any quasi-projective variety. And let's notice in this case that what a section does so that's what our section looks like. These are some sort of regular maps on X. And if I think about it in terms of the coordinate ring of X, this section is inducing a derivation of the coordinate ring, right? Just because this is exactly the condition of being a derivation. So in this case, in this particular example, you would have there exists some f in the field of rational functions. That's a new constant. It's the unless. Okay, so unless there's some reason, and again, you're getting this vibration. Okay. So we see we have a theorem that looks kind of the same. Finitely many invariant guys unless. And I don't know how Rahim came up with this, but this is Rahim's unification. So Rahim's unification is here X so we're going to take an algebraic variety over a field of characteristics 0. Z is going to be an irreducible scheme. I guess I should say X is an algebraic. It's irreducible. And X is an irreducible scheme of finite type over K, but not necessarily reduced. And that's important in this. And we're going to assume we have V1, V2, rational maps. And if I look at the composition, I want these compositions to be dominant. Okay? So this guy in particular is an irreducible variety. Then there exists finitely many hypersurfaces, H and X, where this occurs unless there's a reason why. And the reason why in this case is this. And again, then we see if you pull back a point here, you're getting a hypersurface, and you pull it back here, you get the same thing. Just a minor point, this is scheme theoretic equality here, pre-images. Okay, so let me say a bit about why this unifies the Cantat statement and why it unifies Cantat and Joint. So I guess I'll just leave this picture up, and hopefully we remember the hypothesis, but the point is this guy's a variety, and it's irreducible, and this guy's irreducible, but it's just a scheme, finite type, not necessarily reduced. And it's precisely because it's reduced that we get the Joint result. So let me just look at an example. Let's look at two examples. So first I'm going to look at z equals x. And I'll just look at an automorphism. And we have another map, which is the identity. So this is going to be our phi1, and this is going to be our phi2. And then we're saying exactly that the set of hypersurfaces that are invariant under sigma is finite unless we get a non-constant map to P1 that has this property. Okay, so we have a dominant rational map here. And this is exactly saying that G is equal to G composed with sigma. So it's giving us the Cantat result. It's giving us the vibration. So this vibration is preserved by sigma. And for Joint, I'll look at a special case as well. I'll look at R, let's say a domain of finite type over C, and I'll look at Z being spec so this is a non-reduced scheme, and this is where we see the example. And X is just going to be spec R. And then if we think about the maps this way, now instead of going from Z to X, they're going from R to S. And we'll take one map, which is just the inclusion. R goes to R plus 0 epsilon. And really, this is the image of epsilon squared. And then we'll have a map delta well, this being a ring homomorphism is exactly equivalent to this being a derivation. So saying that you have a ring homomorphism is saying this is a derivation. And if we look at what it means for the ideal of R in S to be R plus delta R epsilon S, that's the case if and only if R divides delta R. So maybe I'll make R a UFD. So then hypersurfaces are exactly, they correspond exactly to the principal non-zero ideals. So then we're saying we only get finitely many of these guys unless there's some new constant, which is giving us the map to P1. Okay? Okay. So my rough plan is to give some idea of the proof, and then I'll give some idea of open questions and some connections to representation theory of algebras. Because Rahim was interested in the question, and I was interested in the question, but they were for very different reasons. And it's kind of interesting how we even thought about this, because we were thinking about it for years and we didn't do anything. And then Adam Topaz came, and we asked him a question, and then he went away and had a kid, and then eventually he had some idea about how to deal with some part of the problem, and that made Rahim and I get interested in it again, and then we worked out a more general case. So let me just show you how the reduced case. The reduced case is kind of like a base case in the induction argument. And I'll just give an idea of how you can do an argument for Z reduced. So in all of these guys, we have our just dominant rational maps. And the first thing you do is you just reduce to things being affine and these guys being regular. So you reduce. Okay, so once you've done that, the other thing is everything is defined over a finitely generated extension of K. So you can assume defined over K, a finitely generated extension of Q. It's not entirely the case that everything is necessarily defined over a finite extension of K because you have these infinitely many hypersurfaces you're worrying about, but you just take Galois orbits of them and you can reduce to finitely generated extension of Q. So we have a lemma. I'm sure it's well known, or maybe someone had done it before, but we did it and we thought it was kind of interesting. Okay, I better do it in order. Lanois, Mel Sanchez, and Moosa. And it says let R be a finitely generated algebra, a finitely generated domain over a field K, where K is a finitely generated extension of Q, or really just of the prime field, the prime subfield. Then there exists R in R, such that when you invert this little R, you get a U of T. This theorem isn't true without this, right? Otherwise, if you work over, say, C, you could take an affine open subset of an elliptic curve and look at its coordinate ring. You'll never get a U of T by inverting a single element because the Picard group is too big. So what that allows us to do is we can reduce to Z equals spec S, X equals spec R, and we can even make R and S U of Ts by shrinking the open neighborhood a bit. And now we're exactly in this setting. And I should say the significance of this is now hypersurfaces are principal ideals. Because all height 1 primes are now principal. So we've got this situation. These are homomorphisms. Wait a second. Let me see what we've got here. So this is R, and this is S. So I've got maps going from R to S. And so we're just looking at this question, phi1r, the ideal equals phi2r. And this is the same thing as saying that phi1r is just some unit if they're ideal theoretically the same. You are. And then this guy is a domain, the UR is in a unit in S. a theorem of Roquette says that the units group of S star is a finitely generated group once you mod out by the guys in the field, the units coming from the algebraic closure. Roquette says that S star mod K bar star intersect F star is finitely generated. So the idea is assuming you have this, you assume you have an infinite set of hypersurfaces is really giving you these principal ideals, and they generate a free abelian subgroup of frac R, and you're assuming that you've got this. So you've got these guys. You can refine it. You can clear out the non-K bar star guy by just using finitely many, using blocks of size the rank at each step. So you can get fractional ideals now so that this So using relations like this and using the fact that these guys are in a finitely generated group, you can take something in the group generated by them and you get things now in the field. And then you're almost done. So I'm going to call these guys now A1. The elements I produce in this manner, A1 through A. So now we have in frac R star, they generate a free abelian group and we have just now, instead of units, we've got it down to field elements. And now we use the fact that this guy has finite transcendence degree. So I know these guys are algebraically dependent. So, for example, let's say 3 of them were algebraically dependent, and maybe I have a relation like this. What I'm going to do is I'm going to take a relation with the smallest number of non-zero terms. And then when I apply phi1, let's call phi1 of ai bi. And if I apply phi1, I get b1 squared, b2 cubed, b3 to the 1 plus 1. I get that. But when I apply phi2, phi1 is now equal to phi2 is going to be b1 squared, b2 cubed, b3 to the 1, but I have to divide by lambda 1 squared, lambda 2 cubed, 3 to the 1. And now what I see is I can subtract, and I can get a shorter relation, because I've gotten rid of the 1. So by minimality, I know that these guys actually have to be the same relation. And that tells me lambda 1 squared, lambda 2 cubed, lambda 3 to the 1 is 1, which is telling me that this guy is a non-constant function that satisfies phi1 of this guy. Let's call this guy G. And because these guys generate a free abelian group, G is in frac R, and it's not constant. So that's how the ideal works in the difference case. So the difference case is the easiest case. In general, what we show is that there's this chain of finite length like this of schemes between z rad, the reduction of z and z. And at each case, we just analyze it step by step, and we work our way up. And we already know that it holds at the reduced case from what we've done. And we go step up, step up, step up. And at each step, you can show that this is somehow equivalent to a system that's like a Johanna-Lu system. And so since we know Johanna-Lu's result, it's not quite Johanna-Lu, it's a little different, but because we can apply the proof for Johanna-Lu at this setting, we can just go up, go up, go up, and we get to Z. And that's the idea. Okay. I'd like to say a bit about why I was interested in this, which is very different from why Rahim was interested in this. So I'll say a bit about representation theory. So let's say you have a non-commutative ring, and when I say non-commutative, I mean not necessarily commutative. Well, one of the most powerful approaches to understanding the ring is to try to instead understand its modular category. But that is hopeless in general. So what you instead would like to do is you'd like to instead work with the irreducible representations of R. And this is obviously a very powerful approach when you use R, say a group algebra for finite group, or commutative ring, where you use these local global principles to say things. It can say a lot, but again, this is hopeless. So it looks bad. So what happened around the 70s was Dixmier said instead of looking at the irreducible representations, look at the annihilators. Irreducible. So if you have a module M, that's a simple R module, I can look at its annihilator, which is the set of R and R, such that R and 0. And a lot is known about this. This is a prime ideal. So Dixmier's philosophy was, instead of trying to understand the irreducible representations, let's try to get a coarse understanding of the representation theory of the ring R by just classifying the annihilators of symbols. So these guys. These are called primitive ideals. And like I said, they're also prime ideals, so they form a distinguished subset of the spec of R. Spec of R. And you've got your primes. You know, they're some sort of poset, topological space, and some of these guys are primitive. And some of them aren't. Right? So you want to understand which guys in the prime spectrum are the annihilators. So it was started by Dixmier and then Moeglin in the 70s. Gave a really nice result. It says that if you have L, a finite dimensional complex Lie algebra, and here UL is its enveloping algebra. So the only thing you need to understand about this is it's some universal object, but this guy's associative. So it's a nice algebra that sort of captures the Lie algebra. Then they gave an equivalence, a set of equivalent conditions for this ring being primitive. The first is that P is locally closed in spec UL. So in practice, that just means that you have your prime P, and you have only finitely many minimal primes directly above it in the poset. Right? If you have infinitely many, then you're not primitive. And this might remind you of the finitely many hypersurfaces, right? It's saying either you get finitely many hypersurfaces, in which case you're primitive, or you should have a family. Two is a little trickier, but you let B be the quotient ring, and then you look at what's called frac B has center C. So what does this mean? This is just some ring. If you have a commutative domain, you can invert the non-zero elements to get a field of fractions. You can kind of do the same thing in the non-commutative world. You invert the non-zero divisors and in a prime Noetherian ring. You don't get a field, obviously, but you get the next best thing. You get something that looks like a matrix ring over a division ring. Simple Artinian ring. You look at the center, it should be C. It has to be at least C. So basically it's saying, you can think of this as saying B is as non-commutative as possible. So there's a purely algebraic characterization in terms of saying it's really non-commutative, and there's a purely topological one in terms of this. And just to give some intuition as to what this is saying is, if you think about a center, Z, that really is corresponding to your fibration and giving you the height 1 primes above P. And P being locally closed is saying finitely many hypersurfaces. So there is some connection. And I'd like to just illustrate it in one special case. And let's say we have a family, a flat family of algebras. Actually, let's see. Let's say it's parameterized by the torus. And let's say that when Q equals 1, you get some commutative guy. So really, we've got this deformation of a commutative guy. That's our family of algebras. So there's a lot of different ways you can go. So you have your family AQ. You can go to what are called Poisson algebras, Poisson manifolds. This is Kontsevich. Let me just say a bit about this. The point is that when we plug in Q equals 1, we recover a commutative object. You should think of this as being like the coordinate ring of variety, and we're deforming the multiplication in some way. So if you look at AB in your AQ, when I set Q equal to 1, I should get 0. So I should be divisible by Q minus 1. So if I look at AB, here Q is generic now. And I divide by Q minus 1, and I take the limit as Q approaches 1, I get something called the Poisson bracket. And I get the Poisson bracket on the classical guy, which was A. And the Poisson bracket also gives me a Poisson manifold, assuming this is maybe regular or something. So the important thing about the Poisson bracket is the Lie bracket. And if I fix an A, it becomes a derivation. And the principle is that one can understand the representation theory of AQ, Q generic, if one understands the Poisson ideals in A. Sorry. So these are ideals where you apply the Poisson bracket, they closed. And if your algebra is finitely generated, you really only need finitely many of these A's. So you've got a finite family of derivations. You can look at the Lie algebra they generate. Understanding the guys that are somehow invariant under these derivations is enough to understand the representation theory of the AQ. So you can reduce this to finite set derivations on A and looking at prime ideals that are invariant. This is very imprecise, by the way. It's not, it's just some philosophy. So somehow these questions immediately become like the invariant hypersurface questions, where you're looking at height 1 prime ideals that are invariant under some derivations. Right? And you can have difference analogs as well if you have difference. So I'll just say in particular, Rahim, Omar, and me and Stéphane Lanois, we use this to show that Poisson algebras of Kroll dimension at most 3 satisfy this Dixmier-Moeglin equivalence by the same philosophy, going through here and then using the invariant hypersurfaces result. Joan goes through. Okay, I've only got a little bit more time, so let me finish with an open question. If you look at Cantat's result, if you try to go beyond hypersurfaces, say codimension 2, now things can go bad. I mean, even if you look at, say, affine 2 space, and you take what's called a Hénon map in a certain family, it's known that it has a dense set of periodic points. And that dense set of periodic points, each periodic orbit is giving you a codimension 2 invariant subwriting. It's an automorphism, so it's completely invariant. So Cantat fails beyond codimension 1. Rahim and Omar, when we were working, they found some Manning kernel example that showed that it fails in the differential case. But in the difference case, there's one case where the algebra suggests that you should have it, that the failure of Cantat shouldn't hold. And that's, I don't have really time to talk about it, but I'll just say the hypothesis. So I'm going to let x be projective, and I'm going to let sigma from x to x be an automorphism of 0 entropy. What I mean here is that I'm going to work with the Neuron-Savary group. I'll tensor it with R. I should be tensoring it with Z, sorry. Maybe I'll just tensor with R. This is a finitely generated abelian group. And I tensor with R, really all I'm doing is just killing torsion. So this is some linear map, and I want all eigenvalues equal roots of unity. And in practice, you can always reduce to the eigenvalues being 1, so unipotent. So we'll say that sigma in this case is quasi-unipotent. And I've got a few more minutes, so I'll just say the question. let x over c be smooth. And suppose sigma from x to x is an automorphism of zero entropy. So this induced map is quasi-unipotent. Then we should get strong Cantat. Then either we get strong Cantat, i.e. the union over all h proper, such that sigma h equals h, closure is strictly contained in X. So it should be hold at every codimension, unless sigma preserves a non-constant vibration. Okay, so like I said, once you get rid of this zero entropy thing, there's things like this Haynon map. Well, you can do things with projective space as well that show that you can't expect this. But there's no known example in the automorphism case. Rahim and Omar tried to adapt the Manning kernel construction to this setting. They couldn't do it. So I should say there are two cases where it's known that this is true. One is if X is a surface or a curve. You can prove it using just the classification, birational classification, and some other stuff. Lefscheid's fixed point theorem. And if this map is the identity or has finite order, there's a theorem of Fujiki and Lieberman that says that, well, you're saying you're fixing a Kähler class, and then there's some theorem that says sigma lies in an algebraic group, and then you can use Chevallier's theorem to get the result there. So it's still, so the first interesting case is E is an elliptic curve. Take E cross E. And if we want to get something of zero entropy, one way of doing this is taking sigma in the Heisenberg group, sitting inside of GL3Z. This will be a zero entropy automorphism. It's not entirely obvious, but it is. And the question is, does strong Cantat, maybe I want to compose with some sort of translation so that it doesn't have a vibration. Does strong Cantat dichotomy? So even for this example, we don't know the answer. So this is the first basic case, and we're interested in it. Anyway, thank you.
Are there any questions for Jason?
Yeah, I have a question. Yeah, okay, so in the differential case, you said, yeah, for codimension 2 or more, it fails, of course.
Yeah.
Yeah, many people know this Manning kernel type example. But there is still a reasonable question, which is, I think open, maybe somebody can say, if X has dimension 2 in that case, like a Manning kernel of an elliptic curve would, then is every such counterexample of dimension 2 in the differential case in finite to finite correspondence with that example?
Yeah, and I think Rahim suggested that maybe that was the case by some sort of minimality. I mean, not minimality maybe in the sense you use it, but
probably.
Yeah.
Yeah, probably. Yeah, but I think that's open.
okay. But anyway, yeah.
Right.
So is the condition of having zero entropy stable by products?
You're saying that if you take X,
Just X times X with sigma times sigma?
it should be, yeah, because should induce just the, I mean, it should, well, okay. The question is, invariance of area of x cross x. Because the invariance of area of E cross E, doesn't the rank go up by, I guess it should be though, right? Well, it certainly should. I mean, I don't, the question is the invariance, in terms of the invariance of area, but okay, it's sort of believed that it should be an if and only, that it should be equivalent to zero entropy. Like you should get, there should be some, in projective space, there should be some family of, or there should be some codimension that witnesses, where you get a dense set. At least for surfaces, we proved that it was if and only if. And then, so then I guess it should be the case that zero entropy is preserved under products of that. We believe that. But, Andy.
If you have a differential curl domain,
Uh-huh.
which is not necessarily you still expect finitely many finitely many differential fractional ideals, hyperlink prime ideals.
Well, we use finite type in a strong way. So you're not assuming that at all, I guess.
I want to ask it as most general as possible.
Yeah.
Any examples?
Yeah, so I would guess once you get rid of finite type, my guess is that you should be able to just construct some sort of, maybe it's like a little contrived, but there should be some examples.
And if it is a finite type, then there are only finitely many.
I believe so.